We are talking about the iron carbon system. In the last video we saw the phase diagram of iron carbon alloy system, a very important alloy system because iron carbon is what gives us steel, and that is the most important engineering alloy. So, we looked at the entire phase diagram of the iron carbon system last time, and we saw that in that system there are three different invariant reactions: a peritectic reaction at a very high temperature, then an eutectic reaction at an intermediate temperature, and finally a eutectoid reaction at a lower temperature. And we said that that eutectoid reaction is one of the most important reaction from the point of view of control of microstructure in iron carbon system. So, we will look at that in detail later. So, at the moment let us look at what do we mean by this eutectoid, hypoeutectoid and hypereutectoid steels. So, this is the lower portion of the phase diagram which you saw last time, and this is the eutectoid horizontal at 725 degrees Celsius. This is the eutectoid horizontal. The phases are above the eutectoid horizontal you have gamma, close to pure iron you have alpha, and towards the right hand side you remember the phase diagram ended at Fe3C. So, this line is moving towards Fe3C, which will come at 6.67 weight%. So, we have not gone all the way up to that point. So, which means now by 1-to-1 rule you have alpha plus gamma here, you have gamma plus Fe3C here, and you have alpha plus Fe3C here in the two phase regions. So, you can see here that if we cool gamma and recall the names, gamma was austenite. So, if you cool austenite of 0.8% carbon gradually such that equilibrium is maintained, then above 725 it will remain austenite or gamma, but below 725 it will become alpha plus Fe3C, it will transform into alpha plus Fe3C. So, this is the reaction which is called the eutectoid reaction. This is what we mean by eutectoid reaction. So, let us write down that reaction. So, we have gamma. So, eutectoid reaction means gamma, that is the austenite of 0.8% carbon upon cooling at 725 degrees Celsius will transform into a mixture of two phases. One is alpha, the ferrite, and another is Fe3C, the cementite. The alpha composition is given by this point here, that is 0.02, and Fe3C composition, it is a compound and its composition is 6.67. All compositions are in weight% carbon, which is what we are using as the unit of composition. So, this is the eutectoid reaction, and this is, we said that this is the most important reaction, most important invariant reaction in the iron carbon system. Out of the three reactions which are present in that diagram, this is the most important one. Now, what will be the microstructure of the steel which has been cooled through this 725? So, what will be the microstructure here? And we can also talk about what will be the microstructure there. So, in the austenite phase field, if you think of the austenite phase field, that is above 725, above 725 degrees Celsius, and let us take an alloy of composition eutectoid composition, which is 0.8. Then this is a steel, 0.8% steel is what is called the eutectoid steel. So, let us note down that nomenclature. So, if the alloy composition is C0, alloy composition C0 is 0.8% carbon, we call this eutectoid steel. Eutectoid steel. So, this vertical line which we are considering, this is eutectoid steel. Eutectoid steel. And then alloys which will be less than, if C0 is less than 0.88% carbon, we will call this a hypoeutectoid steel. Hypoeutectoid steel. So, in this range we will have hypoeutectoid steel, and if the composition is more than 0.8% carbon, we call this hypereutectoid steel. Hyper is more, hypo is less. So, hypoeutectoid is less than, the composition is less than the eutectoid, hyper composition is more than the eutectoid. So, in this range you have hypereutectoid steel. So, this is the nomenclature. So, we are now currently considering the eutectoid steel, that is 0.88% carbon. So, eutectoid, our steel is eutectoid steel, and that steel, if I look at the microstructure above above 725, then I should have a single phase gamma, but you have now studied that although it is single phase, it need not be single crystal, there may be many differently oriented crystal giving you what is called the grains and grain boundaries. So, all grains are gamma, but it is polycrystalline. So, polycrystalline single phase austenite gamma. If you now cool, then at 725 this reaction will proceed and you will start forming alpha and Fe3C. So, if you now look at alpha plus Fe3C, we will get, so somewhere here, let us say below 725 degrees Celsius, same steel, eutectoid steel, we will have a microstructure in which alpha and Fe3C both will form as alternate plates. Now, the phase diagram does not tell us, the morphology. Phase diagram is only telling us that we will have a mixture of two phases alpha and Fe3C, but it so happens that if you look at the microstructure, then you get alternate plates of alpha and Fe3C, and these plates will be oriented differently in different regions. These are called different colonies. So, the microstructure which you get here is, so let us say that the dark lines are the Fe3C and the white region in between is alpha. So, you have mixture of alpha and Fe3C, and this mixture has been given a special name in steel terminology. This has a special name, and that is called perlite. So, this mixture alpha plus Fe3C mixture, this is what is called perlite. So, which means a eutectoid steel which is cooled slowly through the 725 degrees Celsius will show in its microstructure perlite, 100% perlite, entire microstructure will be perlite. But note that perlite is not a single phase, it is not a name of a phase, but it is name of mixture of two phases which have a certain appearance in the microstructure. So, perlite is a micro constituent and not a phase. Let us note that here. Micro constituent, which means it has a certain appearance in the microstructure, but it is a mixture of two phases. Mixture of alpha plus Fe3C.